All right, here we go. We're going to be talking today about universal gravitation. All right. So gravitation is the tendency for bodies. Obviously, bodies have to have mass, right? It's the tendency for two things that have mass to attract each other. Okay. So any two objects in the universe that have mass will be mutually attracted towards each other by a force that we call gravity. So if this is force of object A, if this is object A and this is object B, then we call, one of these forces is the force of B pulling A, and the other one is the force of A pulling B. Okay? Cool. So, things you should know about gravity. It holds us to the Earth. It holds the Earth in orbit around the Sun, and the Moon in orbit around the Earth. It holds the Sun together with the other stars in our galaxy. It reaches across galaxies to hold together what is called the local group of galaxies. All right, and furthermore, it holds together the local supercluster of galaxies. And I am told, although to be honest, at the time of this recording, I need to look up and see what this means. It apparently pulls the supercluster toward the Great Attractor, which that sounds like a Mr. Hernandez question for me. It sounds like deeper astronomy than I know. So anyway, because of all this gravitation, it attempts to slow the expansion of the universe, right? Because as your objects move apart, this mutual attraction tries to pull them back together, okay? And then it's also responsible for black holes and the Disney movie of the same name. All right, let's see. So here's the deal. So gravitational attraction, this force of gravity, depends on the amount of stuff. In other words, the amount of matter that makes up the object, okay? And because the Earth has lots of stuff, lots of matter, the result is that it produces a large attraction, right? That's why we're most conscious of the force of gravity between the Earth and other things, okay? Force of gravity is always attractive. It never repels two objects. Newton realized that this attraction was responsible for maintaining the orbits of the objects, right? We talked about that in honors, about the fact that he was thinking about the moon orbiting the Earth, and he thought, why doesn't the moon float away? Oh, there has to be something pulling it in. Oh, that something has to be gravity, right? And the story goes that he made that realization while sitting under an apple tree. An apple fell onto his head, and he was like, aha, Eureka! Although he probably didn't say Eureka, since I believe that Eureka was a person who existed after Newton. But Eureka might not even be a person. I'm not sure. All right. Okay, so anyway, so Newton's law of gravitation, which is what we're going to learn here in a minute, defines the strength of the attractive force between two particles, okay? And just to give you a little bit of sense, the force of attraction between something like an apple and the Earth is in the neighborhood of 0.8 newtons, right? Whereas for two people, if you have two people that are standing right next to each other, the force of attraction is still less than 1 micronewton, less than a millionth of a newton. Okay? So, anyway. So here it is. If you want to calculate the magnitude of gravitational attraction between two objects, here's the equation. The force of gravity is equal to G, which is the universal gravitation constant, which you should probably memorize because it's going to come up a whole bunch. It is written on your AP test sheet thing, though. Okay. So anyway, so you take that universal gravitation constant, you multiply it by the mass of the two objects, and you divide it by r squared, where r is the distance between the two objects. Okay. Now notice this equation, technically speaking, is represents the force of gravitational attraction between two particles. All right. Like point masses. Okay. So we will, in a minute, we'll talk about, sort of what you do if they're not point particles. All right? All right. Now, it is worth noting that this force of attraction always points from one of the particles to the other. So if you've got, particle 1 here and particle 2 here, then the two forces of attraction are going to be along the line that connects them, right? Because this would be my r, right? Okay? So what this bottom equation does is it basically rewrites it in vector notation. So it says the force of attraction as a vector has a magnitude of this, okay? And then we're going to multiply that by a vector to turn, because this is a scalar quantity, we're going to multiply it by this vector And the vector we're going to multiply it by is the vector that is a unit vector, which remember, that's what this little triangle hat means, right? It means it's a unit vector. In other words, it has length 1, and then in the direction of r, okay? So basically, you're just turning something that's a scalar into a vector by multiplying by 1 and tacking on the direction, okay? So there you go. So that's a little bit of vector mathematics for you. All right. That, if you didn't follow that, not the end of the world. All right. So now, so what happens if we've got something that you know, has a number of particles, right? Like maybe we've got particle number 1 here, okay, and it's got 2 or 3 particles around it. So here's particle 2, particle 3, and particle 4, and we want to find the net gravitational force on particle 1. All right, well, the idea is force 2 is going to pull it this way, force 3 is going to pull it this way, force 4 is going to pull it that way. So to find the net gravitational force, we simply sum up all of those forces, right? Okay? And so then what we do is, suppose you've got an object that is, you know, that's actually got size, right? Maybe we've got particle 1 being attracted to something like a rod like this, okay? So to do that, what you have to do is you take an integral, right? You find the force of attraction between this particle, and then this particle, and then this particle, and this particle, and all the way along its length. And so you can see that you're just taking an integral there, right? Because you're doing basically an infinite sum, okay? So I do think there's one problem like this on your homework assignment. It is labeled as a super bonus question because I don't think that that's something you would ever be expected to do on the AP test. But, you know, worth looking at. All right, because usually what happens is our objects are not usually point particles, but they are usually either uniform spheres or a uniform shell, okay? And so what happens then is you take your giant sphere and you treat it as a point particle located at the center, okay? And as long as your object is located outside of said sphere, then your force of attraction can just be treated as, you know, particle 1 and particle 2 being located here. All right, and then we'll talk about what happens if you have a particle inside the sphere in a little bit here. All right, so there we go. All right, so let's do a quick example because I want to point something out here. Okay, so suppose we're trying to do that. Suppose we're trying to find the net gravitational force on particle number 1 in this example here. Okay. Well, the idea is particle 2 is going to pull it upwards, right? And particle 3 is going to pull it to the side, right? And so I always make this mistake, all right? So you got to be careful here. So whenever I look at a drawing like this, I think, oh, well, particle 2 is going to pull it up, particle 3 is going to pull it to the side, and therefore my net force vector is going to point this way, all right? But that doesn't work because your force isn't proportional to the distance between the particles, okay? So let's do an actual example here, all right? So let's do this. Let's suppose that mass number 1 has a mass of, we'll just call that mass m, okay? And let's suppose that mass 2, I chose some specific numbers here to make this work out relatively nicely. So we're going to make mass 2 have a mass of 8m, and we're going to give mass 3 a mass of 24m. Okay? All right, so what you need to remember is the force of attraction depends not just on the distance between the objects, but on the relative masses of the two objects, right? Okay? So let's do this. Real quick, while I'm thinking about this, if you're looking at your little note packet, ignore these two angles here. These are, I don't know where those came from. Garbage. All right, so anyway, so let's do this. All right, so what I want to do is this. So we've got our particles. So here's particle 1. Up here we've got particle 2. Over here we've got particle 3. Distances between them are A and 2A. All right, so let's find the force of gravitational attraction between particles 1 and 2. Okay, well that's going to be G times m1 times m2 over the distance between them squared. Okay? And then remember, m2 is, what did we say it was? 8m, right? So if you replace m1 with m and m2 with 8m, you get 8 times g times m squared all over a squared, right? Okay? Let's repeat that same process to find the force of attraction between particle 1 and particle 3. All right, well, that's going to be g times m1 times m3 over 2a quantity squared. So replace m with m, or m1 with m, and m3 with 24m. And so you end up getting 24g m squared over 2a squared, quantity squared, is 4a squared. So simplify this, and you get 6 times g times m squared over a squared, right? Okay? So what that means then is this. So this little drawing, this drawing that I've got here, sort of shows the relative distances between the particles, right? Okay? So what we just did now is we found our net forces, right? Or our individual forces. So here's particle 1. Okay? So what this is telling me is that particle 1 is being pulled up by mass 2, right? With a force of 8. Times g m squared over 8 squared, right? Oops, a squared. That's an a. And I should fix it, shouldn't I? A squared. Okay? And this other mass, even though it's significantly bigger, it's farther away, isn't it? Okay? And it turns out that the distance makes a bigger difference. So this force is actually a little bit less. So the force on particle 1 from particle 3 is only 6 times g m squared over a squared, right? Okay? And so now we can do our vector addition, okay? So vector addition, this becomes 6 g m squared over a squared. Vertical component is 8 g m squared over a squared. And so my actual net gravitational force on particle 1 is going to be, you know, this. So you got to do some vector addition. You can see I chose my numbers, so this works out to be a 6, 8, 10 triangle. So you're going to get 10 g m squared over a squared. And then you can find your angle here using a little bit of trigonometry. And I think that turns out to be 53 degrees. So above the negative x axis. All right? So that is that. Okay? Now, another quick thing that is probably worth commenting on. I'm going to be upfront here. I hate this chapter. Because what ends up happening is your masses end up being super huge, so you get scientific notation. G is a gravitation constant that's times 10 to the negative 11th, and all the scientific notation becomes kind of a pain. So I try as much as I can to write things like this, and I just leave G as a variable, and then when I need a numeric answer, then I multiply it in at the end. Okay? Just a suggestion. I know some of you prefer numbers over variables, but you know, I do think that will make your life a little bit easier. All right? Now, so if we remember this, so we know that the force of gravity on Earth is equal to mg, right? I don't like that I have this written here. And we know that the force of gravity is g. So on Earth, sorry, so, all right, I'm totally skipping a step here. So suppose you want to find your force of gravity on Earth, all right? Well, your force of gravity on Earth is going to be equal to, well, what are the two objects? There's, so gravitational constant times m, which would be your mass, times the mass of the other object, which is the Earth. Let's use capital M to represent the mass of the Earth, over the distance between your center and the Earth's center, which is basically the radius of the Earth squared, right? Okay? So if you set these two things equal to each other, what you see is that m's cancel, and we discover that g, the acceleration of gravity on Earth, is g times m over r squared. Okay? So here I've written it using ag just to represent the generic acceleration of gravity on any generic planet. And so here m is the mass of said planet, and r is the radius of the planet. Okay? So what that does is it gives us the magnitude of the gravitational acceleration at a given distance from the center of the Earth or arbitrary planet. All right? So I think everything here we had done so far last year, maybe except for the vector addition, right? Okay, so this table down at the bottom here shows you the value of the acceleration of gravity for various altitudes above the Earth's surface, right? Because as you get farther away from the Earth's surface, there's going to be less gravitational pull. All right, so the average gravitational pull on the Earth is 9.83, okay? So that's assuming you're at an altitude of 0, okay? And actually, that might not be right. Yeah, okay. Anyway, so on Mount Everest, because you're very, very high up, your acceleration of gravity is going to be 9.8. The highest crewed balloon was, at the time that this book was written, highest acceleration of gravity was 9.71. I think that has since been beaten, right? Because that one guy just recently built that balloon that took him up to the limits of space, right? So what would that have been in 2016, right? All right, let's see. In Space Shuttle, there's still gravity for astronauts in the Space Shuttle, right? It's just that the astronauts in the Space Shuttle and the Space Shuttle itself are falling at the same rate. And that rate happens to be about 8.7 meters per second squared. Communication satellites, which are geosynchronous, which means they have the same, ooh, I should double check that, but I'm pretty sure those are going to be geosynchronous communication satellites, which means they always stay above the same point on the Earth as they go around. Okay, so their acceleration of gravity is just 225. Okay. All right. Yeah. Now. Oops. So here's the deal. Because the Earth spins, well, for a number of reasons. It turns out that the calculated acceleration of gravity is going to differ slightly from the measured acceleration of gravity at any location. These symbols are a little bit wonky, so don't get too concerned about these. All right, but so when you calculate the acceleration of gravity using, the equations that we just learned, and you measure the acceleration of gravity at any location, those numbers might not be the same. All right, and the reason for that is this. One, the Earth's mass is not uniformly distributed, as is seen in this chart down here. Secondly, the Earth is not a perfect sphere, right? It's got mountains, and it's slightly oblong, and, that kind of thing. And it rotates, okay? And so that causes the acceleration of gravity at different points to be different, okay? And here's that density graph. You can see that the density is higher towards the center, which makes sense because of gravity. And the farther you get from the center of the Earth, the less the density is, okay? All right, so I want to do one quick example here, all right? So look at this. So here we've got a top view of the Earth, okay? North Pole, so the perimeter of the circle would be the equator, and we've got this crate here, okay? All right, so let's take a minute and calculate how much the scale in this little drawing here is going to read, okay? So in other words, so the reason that we sort of have weight is because we're conscious of the normal force pushing us upwards, right? So a lot of times when we talk about, feeling weight, you're actually feeling the normal force on your feet, right? So that's sort of your perceived weight, okay? And then gravity is pulling you down, okay? So let's think about what's going on here, all right? So the idea is this. If you're standing at the equator, so here you are at, my geography is so bad, but whatever, you're standing in whatever country is located right there, all right? And the Earth is spinning around, let's see, it's going to be spinning around this way, right, because east to west. So you're moving in a circle, right? Okay, so let's see. Oops. All right, so here's what we know. So at the equator, here are some things that we know. Well, I guess this is true not just at the equator, but so the radius of the Earth is somewhere in the neighborhood of 6.38 times 10 to the 6th meters. You know that the rotational period of the Earth is 24 hours, which, if you're keeping score, is 86,400 seconds. And we are going to need this capital M, as in the mass of the Earth is 5.98 times 10 to the 24th kilograms. Earth is really big, you guys. All right, so the idea is when you're standing at the equator, you're traveling in a circle, right? And so remember, the velocity that you experience when you're traveling in a circle is just 2 pi r over t. Okay, so plug those numbers in here, and you end up getting a velocity at the equator of 464 meters a second, right? Okay, but keep in mind, you're moving in a circle, right? So that means that you are experiencing centripetal acceleration, and there has to be a centripetal force causing that, okay? And in fact, that's really your only acceleration, right? Because your tangential velocity is constant, so all of your acceleration is centripetal, okay? So our centripetal force should equal our net force. Oops, let me write this a different way. So our net force is going to equal our centripetal force, which is just mv squared over r, right? So if you use this v and this r, you'll find that your centripetal force, when you plug these numbers in, is 0.0337 meters per second squared times whatever your mass is, right? ma. Okay. All right. So what that means is that when that crate is on the scale, or when you're on the scale, I guess, whatever, here's what's going on. So let's see. So here's your object. All right. So gravity is going to pull it down, right? Well, let's take a quick second and find that force of gravity. Okay. So force of gravity should be g times the mass of the Earth times the mass of you or the crate or whatever divided by r squared. Okay, this is worth doing. Like, plug this into your calculator. You're going to use g, remember, is, well, it's in your notes, but I'm going to write it down anyway, 6.67 times 10 to the negative 11th, what is it, Newton meters squared per kilogram squared. So plug in g, plug in m, leave lowercase m as a variable, and plug in r, and you end up getting 9.799 meters per second squared times this m here that we didn't know, right? Okay, and notice, this is the acceleration of gravity, right? This is basically just mg, right? Okay, where g is the accepted value of g, 9.8, right? Okay. All right, so now what we can do is figure out what's going on, right? Sorry, I got to finish my drawing. Okay, so this is, sorry, let's just call it 9.8 g. Well, whatever, we'll call it 9.799 g. Cool. And what we're curious about is what that normal force is. What does the scale read, right? Well, we know that our net force has to be this value, right? 0.0337 m. Oh, this is wrong. Sorry. I put 2 g's in there. That should be an m, right? So it's m times g. Okay? And our net force we figured out was this. So let's see. Let's check our signs. Our net force has to be downwards, right? Towards the center of the circle. Force of gravity is downwards. So now if I do, basically, this is net force equals net force, right? So our net force has got to equal Fg plus Fm. So 0.0337 m equals 9.799 m plus our normal force, and solve for it. And your normal force ends up being 9.765 meters a second squared times m. Okay? So what that means is, at the equator, the acceleration of gravity is a teeny little bit less, right? Because some of the Earth's gravity is used to provide the centripetal force to prevent you from spinning off of the Earth, okay? And then the remainder of that is seen as acceleration when you drop a ball or whatever, okay? All right. One last thing here. So if you're thinking, wow, this is a long video, this would be a good place to pause it and come back and finish later. If not, I'm going to just muscle on through. So the next thing we need to talk about then is what you deal with, how you deal with the fact that sometimes objects could be inside the Earth, okay? So this question is sort of prompted by what would happen if we dug a very, very skinny hole through the Earth and we jumped into the hole, okay? All right, so we've already learned how to calculate the force of gravitational attraction if you're out here, right? That's just going to be the g times m1 times m2 over d squared, right? Okay, so, but what happens when you're inside the Earth, right? So it turns out, and this is not too surprising, that if you're at the very center of the Earth, if you're right here at the center of the Earth, hypothetically, there's like a little teeny, spherical room and you're inside it, there's just as much mass above you up here and below you down here, and so the force of gravity pulling you upwards cancels out the force of gravity pulling you downwards. And similarly, left and right cancels out left and right, okay? And so the net gravitational force on you here is 0, okay? And so the idea is then, when you're here, say, now there's more mass below you pulling you down, right? When you're here, there's more mass above you pulling you up, okay? So how do we deal with the fact that that changes as you go through the Earth, okay? So a couple things. So first of all, it turns out this is what is called the shell theorem, all right? This is super duper mega crazy important. The shell theorem says, and I'm actually going to get myself a new page here. It turns out if you've got a body, like suppose we had a giant volleyball or a giant basketball, right? Some giant hollow sphere, okay, the size of the Earth, okay? And then we set up residence inside said basketball, all right? It turns out that no matter where you are inside this giant spherical basketball floating in outer space, it turns out that the net gravitational force on you is going to be 0. Okay? Proving that requires a fair amount of calculus, but it's true. All right, so I'll give you a real quick explanation. So if you kind of do, like picture this dude here, right? Okay, so there's a little bit of mass below him, but he's very close to that mass, right? Okay, and then if you look at all of this mass up here, which I will now color in blue, there's a lot more of it, but he's farther away from it, right? Okay, and so it basically turns out that the force pulling him up cancels out the force pulling him down, and so the net force is 0, okay? And that works at any point inside the sphere, okay? So that is called the shell theorem, okay? Inside any, uniformly distributed shell, the net gravitational force is 0, okay? So that is the shell theorem. Okay, now, so let's see. So this first little paragraph here kind of talks about what we've already done. So if you've got a uniform spherical shell of matter and your object is outside of the shell, then you just use, your usual universal law of gravitation equation, right? Because so here's your shell, here's you, hello, right? This shell can be treated as a point acting here, and so you just use, Fg equals g m1 m2 over d squared, right? Or r squared, or whatever you want to call it, okay? It's only when you're inside the sphere that you need to worry about it, okay? Now, what happens if you have a solid sphere that you're inside, which was our original question, right? So here is the deal. So let's go back to our little drawing here of the Earth, all right? And let's suppose that your mass is right here as shown, okay? So what you're going to do then is you treat this as two different things, all right? So let's imagine that the Earth, let's break the Earth up into two chunks. So let's split it up along this little dotted line here, okay? And the idea is everything outside of the dotted line, all of this is a spherical shell, right? And so the net gravitational pull on you from all of that garbage is 0, right? So now all I need to worry about is the force of gravity from everything inside the sphere. So I got to worry about all of this stuff, right? Okay? So now what I basically need to do is I need to use, Fg equals g times, well, what? Let's see. I would want the mass of all of that garbage that's inside the shell, everything I just shaded in black, times your mass over little r squared, where this is little r, okay? Okay, and so what we're going to do is we're going to call this big R. All right, so the math is kind of worked out here on the screen. I don't know that it's really that relevant, but basically it boils down to, if you assume that your sphere has constant density, which is the only way that we would be able to solve this, or we'd need, to use some more calculus. So the density is going to be the mass of the inside over the volume of the inside, which is 4/3 pi r cubed. That's got to be equal to this, right? Okay, and so a little bit of algebra, where you substitute this in up here, shows us that at this point, where this little red dot is, the force of gravity is equal to the force of gravity at the surface, okay, times sort of the ratio between your radius and the actual radius of the Earth. Okay? All this stuff about Hooke's law, I think I'm not going to worry about this right now because it's sort of a weird side note that's not super important. Okay? So let me run through a real quick example, all right, which I am going to make up right now. All right, so suppose we've got a planet which has a mass of, I don't know, let's say 5 times 10 to the 24th kilograms. And let's suppose it's got a radius of 7 times 10 to the 6th meters. All right, and let's suppose that you have a mass of, let's say, 100 kilograms. All right, why don't you pause the video for a second and answer these 3 questions. Find out how much you would weigh if you were, let's say, 1,000,000 meters above the surface. Find out how much you would weigh at the surface. And suppose you were 1 times 10 to the 6th, 1,000,000 meters below the surface. Okay? And we're going to assume that it's of uniform density. All right, so take a second, pause the video, see if you can figure those out. We'll be back. All right, so to think about this, I guess what we should do is this. So let's make a quick drawing of the planet. So the radius of the planet itself, we said, was 7 times 10 to the 6th, right? So in part A, if you're 1,000,000 meters above the surface, that's going to make the radius for part A would be another 1,000,000 more, so 8 times 10 to the 6th meters, right? So to do part A, to find your force of gravitational attraction, you're going to do G times the mass of the planet times your mass divided by that r squared, 8 times 10 to the 6th meters. Don't forget to square it, and you end up getting pretty close to 521 newtons. Okay, so that's part A. Okay, part B is actually probably the easiest of the 3, right? Because you're doing the same thing, but you're just using the radius of the planet as your r. So there, your FG is going to be G times 5 times 10 to the 24th times 100 all over 7 times 10 to the 6th squared. And so you get 680.6 newtons. All right. And then finally, part C, if you're this far below the surface, well, that means that your radius is going to be a little bit less, right? Okay, and so what we learned was that you could calculate that by finding the force of gravity at the surface, which is G times 5 times 10 to the 24th times 100 all over 7 times 10 to the 6th squared. But you multiply that by the ratio you're at, or sorry, the radius that you're at. So if you're, 1 times 10 to the 6th meters below the surface, your actual radius from the center is going to be 6 times 10 to the 6th. So many numbers. That's your radius over the radius of the planet. Okay, and solve that. And you end up getting 583.4 newtons. All right, so one last question. Let's suppose that this planet, instead of being a solid sphere of uniform density, let's do this exact same question as if the planet had been a hollow shell with the same mass and same radius that I originally stated. Okay, so now the planet's hollow. Okay, recalculate the answers for each of those 3 problems. I'll give you a minute to do that. Hopefully you have paused the video and done that. So it turns out that doesn't affect the answer to part A because you're outside of the sphere. And it doesn't affect the answer to B because you'd be at the surface of the sphere. It only would affect the answer to C. The answer to C would become 0 because of the shell theorem. All right, there you go. Universal gravitation.